Okay, hi everyone. Welcome to another group meeting for the Spark Lab. Today we have a guest speaker. I'm very excited about this talk. Our guest speaker is Benjamin Morrell. Ben is a robotics technologist at JPL, working on autonomous navigation technology for robots flying, exploring underground and in space. He's currently the perception lead in Team CoStar, which is a JPL, MIT, and Caltech team competing in the DARPA Subterranean challenge. So many in the group know Ben and are having the pleasure to work with Ben and many other colleagues at JPL on SubT. Just to provide a little bit more context, so Ben is doing an excellent work on CoStar. Previously, he was at JPL as a postdoctoral researcher after completing an internship at JPL during his PhD. And he did his PhD at the University of Sydney in the School of Aerospace and Mechanical and Mechatronic Engineering. Sorry, Ben. So the PhD thesis from Ben was focusing on autonomous navigation for radial and space-based robots, considering localization, mapping, and trajectory planning and control. I didn't realize, but when reading the bio, I realized that Ben also spent some time at the Space System Lab at MIT, working together with a team on spheres, which was very interesting to learn. And in addition to his core research, Ben has been also involved in a range of activities, including 3D printing, in Mars mission simulation, and coordinating the Zero Robotics competition in Australia, where, as you know, high school students get the opportunity to send their code to the International Space Station. So I will stop here and just leave the stage to Ben, but I just want to thank you, Ben, for being here and giving this presentation. In other circumstances, we would have some round of applause here to welcome you. You have to be happy with the virtual version of it. Take it away.
Thanks, Luca. No, it's great to be at. Oh, thanks for the virtual applause. It's great to be able to be presenting to your group. It's exciting as well because I think all the things that you guys are doing is really always great to see and see updates on. And so it's a fantastic group. Exciting for me to present to because I'm excited to share what we're doing, excited to kind of get your questions and insights on what we're doing. So feel free to send questions through chat. I can try to get back to it at the end. But also if you've got a question like that's makes most sense to us, then please feel free to interrupt me. I'm fine with that. So no worries on that. We've also got Matteo on the line, who's one of the awesome people at JPL, intern there at the moment, who's done a lot of the great work that I'll be presenting. And so I've kind of put this together. I'll be going through it, but Matteo's there to answer questions that I might throw to him for a few extra comments on some of the great work that he's done. So thanks for joining, Matteo. So I'll share my screen now and get the presentation up. So I'm a little bit normally I get Q&A back as I'm presenting, but a little bit hard to get here. But I'm guessing that most of you know what NASA is. And if you don't, feel free to kind of unmute and speak up and explain that. Maybe less people know what JPL is, and often it can be a little bit confusing. So just kind of give a little bit of context to that. So it's called the Jet Propulsion Laboratory, but we don't really do any jets or propulsion. There's a little bit of work on electric propulsion, but really JPL is most known for robotic exploration of the solar system. So rovers on the surface of Mars is the most famous, but also orbiters that go around different planets such as Cassini, or beyond the solar system such as Voyager. And I didn't quite really appreciate it till I saw the diagram a bit like this. Every one of these lines is a mission that is sent into space to explore the solar system, a robotic mission from JPL. This is not just NASA, this is JPL, the one organization. And each of these lines is going out to explore the different planets, to go explore asteroids, to explore comets, for astronomy. So it's a really kind of rich history of these robotic spacecraft going out. But one of the more recent ones that is really exciting, you may have seen the video recently. I'm not sure that audio is coming through for you guys. But on the next Mars rover, Mars 2020 rover, it's going to have a very interesting payload, the Mars helicopter. This is a technology demonstration mission to see, can we fly on the surface of another planet? And can we fly Mars? And what's capable? So it's a solar-powered system, very large rotors, taking off, and using much of the similar technology that you guys are used to in terms of visual navigation, doing VIO, for tracking its state to control itself. Do some simple maneuvers to show that we can fly around. See the two cameras facing down. One's a science payload, one's for VIO. And this is to really pave the way to show we can do this. And they'll be launching on the next Mars rover. So it's pretty cool technology, and it's obviously an animation, but this is the final test of flight version at JPL. So this is in a vacuum chamber where they pump out the atmosphere and to vacuum and then put in CO2 to match the Martian atmosphere. There's then a little cable you can see at the top that is doing a gravity offload. And here it is just hovering in as close to Martian conditions as we can replicate on Earth and showing that it is flying on Mars. So it's quite a good feat. And this is the actual flight hardware that's now on the bottom of the Mars rover in Florida, getting ready to launch in June. I think it's June or July. This is really exciting technology. But one of the points I wanted to make here is that this amazing thing of a helicopter flying on Mars doesn't just happen overnight, like you expect, but it doesn't just kind of suddenly be a project and happen. It is built off a lot of technology development to develop different parts of the visual inertial navigation system, the different control systems, the different software. And that builds together to give a capability to JPL to be able to create these types of systems and these types of ingenious, it's called ingenuity, or advancements in what we're doing. And so it's really that technology development, which is a big part of what JPL does. And that's what I do. So what I've gone over is a bit of an introduction to JPL. I'll talk a little bit about who I am and what I do. And then I'll sequence to one of the big current technology development work that's looking to build that technology for future missions like future helicopters or exploring caves. And that's the DARPA challenge. And Team CoStar is the team that I'm involved in, that Luca and Ewan and the team at Spark are involved in. I'll go through an overview of the system and feel free to throw out questions if you want more details on that. But then I'm going to be focusing on the perception system, particularly the Lidar Odometry, that's Matteo's baby, and LAMP, that's a larger kind of an architecture for SLAM, which we'll get into details of. So background to me, this is the university I went to, and I got a degree in wizardology. So obviously I'm joking there, this is not Hogwarts, but this is the University of Sydney. This is a quadrangle. So just like you have a beautiful building at MIT at the start, this is our kind of our main building, which you only ever go into for graduation, really. And so there I did my undergraduate degree, which is in aeronautical engineering. And from that, doing my PhD. So working with this field. So this is what Luca was saying. Now my supervisor was Greg Chamatoff, who was a former astronaut. So when he can get back to MIT, he's plastered on the wall somewhere floating in space. So check that out there. But there's some great insights from him, and also spent a year at Texas A&M University. From there, I think Luca gave the introduction, but the focus has been on robotic research, and that's what I'm doing in the Subterranean challenge. And so the challenge, I'm going to go a little bit over it, but feel free, please do unmute and go in if you want more details. So I'm guessing you guys have a bit of an idea of what this is. But this is the third of the grand challenges and of DARPA for robotics. The first one really spawned autonomous cars. The second one was humanoid robots, and this is the third. So we've got different types of underground environments, and it's pretty much a search and rescue context. So we have caves, we have mines, and we have the urban underground. What we're trying to do is go and find some sign of a survivor there. So it could be a cell phone, a backpack, a tool, some climbing equipment, or find a person themselves. And so the challenge is set up to have a single operator. So the idea is that it can be really push the autonomy to rapidly search and find these things, because it's going to be a disaster scenario. So it's 1 hour. It's going to be a previously unknown environment. And so the idea there being we can adapt to any type of environment wherever a disaster may strike. And then the information on where we find these, what they call artifacts, so the people or the backpacks or the cell phones, report them with a location back to the base station. So the idea there is like someone who's going to be responding and going to rescue these people, like the human rescue team, they know exactly where it is. And so that's the context of what we're trying to do in the competition. And the competition is set up to reward teams that do that. So that's Team CoStar, and COSTAR is an acronym, which honestly I forget, but it is that collaboration, mainly between JPL, Caltech, and MIT. We also with collaborations from KAIST and Luleå University of Technology. And this is the team at the tunnel competition. And so there's a few things to point out here. First of them is Yun, if you can spot him there. And bonus points if you guys can spot everyone else that you know. There's Luca, and there's me before I had a haircut. The main robots we were relying on here were these Huskies. They were kind of the main ones that were scoring us points. We also had this system here, which is kind of like it's a remote control car that's been modified, but with the same kind of sensors and computation and algorithms as the other robots, with some modifications, and then some of the drones and some hybrid mobility. Those ones are more kind of in development. And then you see the actuated track back there. So those are the main robots we were having during the tunnel competition, which was the first one. That was in August of last year. But now for the urban competition, and what we're mainly focusing on at the moment is the Huskies, same robots there, as well as the sport robots, the legged robots. And they've got the same type of systems on them. They've both got Velodyne Lidars. This one's Huskies have 3 for better traversability. Real sense cameras you might be able to spot here. This is a enclosure for a thermal camera for detecting people. There's also a gas sensor. That's one of the things we have to detect, and then a computer, big kind of boxes for the computers on them to do all the processing. So what I want to dive into and spend a little bit more time now, and again, feel free to jump in if you have questions at any point, is kind of the system. And there's many ways to represent the system. It's a full robotic system, robotic system. So it gets a bit complicated, but this is one way to look at it. And the world model here we're describing is basically any shared information, such as maps, or what we have as a roadmap, which is kind of like it's a graph that represents where we've been and where we want to go. And I'll step through each of these, but we'll spend more time on perception. So breaking out these boxes into some more details inside, let's first look at autonomy. And so these 2 parts are kind of the main autonomy services. So the mission executive is basically giving the high-level commands or tasks for the robot. So imagine the task is go and explore. There might be a mission that has a set of states that might sequence between depending on what happens. So the first state might be go and explore, and that explore is a behavior in the behavior engine that I'll get to. And then if it reaches some component, like it's detected that it's at a dead end, then it will sequence to another state, which might be another exploration behavior. It might be returning to base. So that's kind of on the mission level. When it sends that task explore, it's a behavior. And that behavior includes a set of different actions, which might be driving in a certain way, doing some type of search of where to go, or it might be dropping a communication node or standing still and waiting for further actions. So those are the behaviors, and that's still kind of higher level, kind of in terms of the actions. But the behavior to explore comes down to what you probably know more is the mobility services. So that's all the planning and control side of things. So first of all, it's the global planning to tell the robot where to go for exploration or to go to a particular location that has been sent. It's then the local planning, given the environment around and the hazards that there are, and then the control. Coupled with that is what we call the roadmap manager. So think of the roadmap as like a connected set of breadcrumbs of where every robot's been, as well as some additional breadcrumbs that are placed in the environment as frontiers to go and explore. Now, I haven't gone into too much detail there, but I'm happy to talk about it more afterwards, but just trying to give you a general idea of that kind of, it's a roadmap global planning with frontiers to explore, triggered by behaviors, and the different behaviors are managed by some type of mission, which is a set of different states. So communications is another really big thing for this challenge, especially for environments like the mines, where you basically turn a corner and your line of sight communications, if you don't have line of sight, you lose communications. So managing that to both maintain communications as much as possible. But firstly, like if we are in comms or we're coming out and out of comms and back into comms, we want to make sure that we are sending the right information and sending it efficiently and making sure we don't drop the information. So we use ROS2 as kind of the communication backbone there for the delay tolerant communications. And we use communication nodes that we drop off from the back of the robots, like you see here. that we place them at different locations around the environment. At the moment, based on the operator, but we're trying to make that autonomous as I guess, nodes on a mesh of communications. So we can always maintain comms or maintain comms for as much as possible. Why do we want comms? To be able to control the robots, yes, but because the whole idea is to get back the information that we explore to the base station, to the human supervisor. And so that's the whole reason why we're doing everything. So that communications is really important for that reason. And so the human supervisor is who's the goal to get the information to, but they also can manage normally sending certain missions, as well as monitoring the health of the system, so they can make decisions on what to do for the robot. So for instance, this is Kyung, this is the operator. Think of him as, in terms of the context of what the real application of this is someone who's going to respond to certain scenarios. So for instance, he might see, oh, okay, I found a survivor, I found a person. So then planning how to send in the rescue team. Or maybe he's found that there's a particular corridor that he wants to explore. And then that corridor can be something where we want to get more information. Maybe it's interesting, he thinks there's going to be more people inside there. Then there's maybe the robot's done something wrong, and or maybe it's stuck and he needs to send it a new mission. So there's some robot responsive stuff to get the robots exploring. Or it might be something like, okay, we found some stairs, go send in the spots or send in more robots because there's more to explore. So there's the kind of like high level decisions the operator's making. What we're going to focus on now is the perception side of things. And so it's got both local perception, which is high rate state estimate for control, as well as a local map of obstacles. The global side of things, which is getting our location with respect to the very start with low drift, as well as a global map, and how we detect these objects and give their global location. So this is, I know, quite a busy diagram, but we'll step through it and it should be relatively clear. And this is building from stuff with Luca earlier on. But let's start off at the top. We have the sensors. So a Lidar sensor, some visual or thermal sensors, some wheel sensors in terms of wheel odometry or kinetic odometry, and an IMU. So they're kind of the inputs to what we're doing in perception, and the outputs are all these products down the bottom. So an obstacle map, a state estimate at high rate, global point cloud, as well as the global location and the artifacts. And within this, the different sensors, we have the different algorithms for processing the sensors, such as VIO or LIO. And then we will combine them together to get a state estimate, use some of that information to get our global location. So I'll go into those in a little bit more detail. But first, I want to draw your attention to this part over here, the object detection. So that takes in sensor information from Lidar, from visual, and is detecting these objects. I'll touch briefly on that just so you have a bit of an appreciation of what's going on. So this is a slightly older pipeline, but this is the idea here, that we have images coming into a deep neural network. This is YOLO that we use, and it's adapted for the specific task. We also have thermal images coming in. Those images, along with their detection, if we have a detection, are sent to a separate module, which is on a different computer, which is running artifact localization. And that localization is basically combining all observations along with the depth measurement or LiDAR measurement to get a relative location, and then adding that to our global pose graph, which we get to get a global position. That then goes to a user interface, which is presenting the report to the operator. And so because we're training for a specific set of objects that we know, and we try to get a lot of images in representative environments, and they use that to train an existing network that's already trained on something like Coco, but train it for that specific application. And so it's kind of an adaptation, a rapid adaptation of an existing network for the application. And so you can see some of how it's operating here. If you see the cameras at the top, there's a fire extinguisher there that was detected in the right camera. And in the bottom is the 3D map. And it will pop up on the map as a green sphere, sorry, a pink sphere here, as well as a report pops up on the right-hand side for the operator. There's a backpack that just came through in the front camera and right camera. Once we've satisfied we've made all the observations, it appears in the map and we get a report. And so that's kind of the process. You saw a survivor pop up here. We detect that, we get the report and we place it in. So it's an example of kind of how that system is working with the addition of thermal cameras now as different types of sensors. So next I want to focus on the state estimation. And this is trying to draw on a concept of in these environments, we have to be really robust. We're expecting things to go wrong. And so we might have multiple sources of odometry, such as visual inertial odometry, Lidar, wheel inertial odometry, and thermal inertial odometry. But we're expecting that they may fail in different scenarios. So perhaps visual, we're in an environment that's very large and we don't see many walls and it's dark, so we can't really see much in the features of, there's not many features to track, so it deteriorates. Maybe thermal inertial odometry is good for a bit because it can see further, but it maybe drops out because there's no thermal gradient, so everything looks the same temperature. Lidar inertial odometry, we ideally can work a lot of the time, but maybe there's a tunnel that's very featureless and we don't get any information there. Wheel inertial odometry should be good for a while, but it's probably not very accurate, so we don't want to use it. But if we switch between these based on which ones are the best and which ones are available, then we can get a reliable output. And that's the idea. So we have ways of checking our confidence of each of these sources, and then a way to switch between the streams based on the confidence levels. And so what it relies on here is these confidence checks on the sensor output, as well as the output from the odometry algorithms. And this, if you want more details, is in a paper called HERO by Angel, which discusses that approach. So we call it heterogeneous robust odometry, HERO, and that kind of gives us a reliable odometry output. Next, I want to jump onto the Lidar, and this is looking at the Lidar front end, and this is what Mateo's been doing some amazing work on. And the idea here is we've got two robot positions with two consecutive scans. Let's assume our scans of Lidar are going at 10 Hertz. We want to compute the transform between them. And so it's a rigid body transform, 6 degrees of freedom. And so basically we use ICP. So you get the two scans, you do some alignment to find the optimal alignment for them. Now, it's a bit more complicated than that though. Now this is the diagram of how Lidar odometry front end comes in. And Mateo, feel free to jump in if there's more details you want to add here. Basically, we have two Lidars that come into what we call a motion distortion correction. So as the Lidar does a scan in 0.1 seconds, we may move in that 0.1 seconds. And so that will distort the point clouds. So we want to correct for that based on our estimate of our movement. We then merge the point clouds, we filter them, and then put them into the Lidar odometry side of things. Now, the main steps here are the scan-to-scan matching and the scan-to-map matching, which are two sets of ICP. But we also have this health monitor after input from IMU and odometry. So what that is we can use odometry and IMU inputs to give an initial guess for our GICP. The other modules here, which we'll get into details of what these are the main three boxes here. If we just draw around these ones, these are the main three parts. OSD is an open space detector to adjust our filtering based on the environment. And this is a module that if we are on flat ground, we can restrict the ICP to maintain us on flat ground. So it simplifies the problem a little bit. But what it comes down to is a three-step process. There's the external odometry and IMU, which let's assume YK is a 6-DOF pose at the previous Lidar timestamp here, and then the current Lidar timestamp. So we just get the transform between them at the timestamps of the two Lidars. And so this odometry could be visual odometry, Lidar, could be wheel odometry, kinetic odometry, or just IMU, but the IMU obviously doesn't give us translation. And that gives us an initial transform estimate. We then use that as the initial guess in this first ICP, which is an optimization to find the transform to minimize the distance between the previous scan and the current scan. And then with that result from the scan-to-scan matching, we do scan-to-submap matching. So SK is a submap, so we build a map up as we go, and we can match to a local section of that previous map. So we're finding the optimal transform to align the current scan to that previous map. But we initialize that with the result from the scan-to-scan matching. And what this sequence of transform computations is really an architecture to have very accurate and robust scan, or I guess Lidar odometry, because each initial, by seeding the previous step into each ICP, it Both makes it more accurate because it puts it close to the solution to avoid local minima, but makes it also more efficient because it doesn't require as much computation to optimize because it's already close to what the solution is. And so this three-step process kind of refines it slowly, but at a kind of a low computational cost. I was able to get fairly accurate results. And so just to show you some performance, this is the SubT nuclear power plant that was never commissioned, so we're not worried about nuclear radiation, but this is where we tested. This gives you a bit of an idea of the types of environment that there are. And so you see it's kind of tight indoor environments, fairly, a lot of, think of like an indoor industrial complex with some rough terrain, some tight corridors, some big open spaces, some very self-similar corridors as well. So some interesting environments in which to explore. I'll just give you an idea of like the environment in which we are doing testing on. So this is from the urban circuit competition. Sorry, I pressed the wrong button there. And so here's the performance. This map is a color scale of the error compared to a ground truth map that DARPA provided. And so yellow is low error, blue is high error. LOFE is our Lidar front end. And it's shown to be pretty accurate there. And the cartographer is also quite good, but has some drift. This is a Google cartographer. And this is loam. So we're comparing against some of the leading open source algorithms out there. They could be tuned more, but initially we're showing pretty decent accuracy there. One of the really important points is the robustness. And so we're testing what happens at this point when we have wheel inertial odometry failure and IMU failure. This is loam on the left, cartographer in the middle, and LO front end, our algorithm on the right. I've shown LO front end handles it fine. It just reverts to pure Lidar odometry. So we just lose that first step. Whereas these other algorithms are waiting for that information. And so they're not able to continue. Similarly, if we just fail the odometry source, this is on Huskies, so this is using wheel inertial odometry, then that's fine for loam that can't take odometry input, but cartographer is not that robust. It's waiting for all measurements from wheel inertial odometry, IMU, and Lidar to be able to do the computations, whereas we're a bit more robust that if it's not there, we'll just switch back to using purely IMU or purely Lidar. And then we're also testing what if Lidar drops out for a little bit of time. And so in that case, similarly for cartographer and loam, it's waiting for both Lidar and IMU to be able to do the computations. And so not able to handle that gap of 10 seconds of Lidar. Whereas LO front end separately accumulates the odometry from wheel inertial odometry. And then with that accumulation, it starts off from a good estimate when it gets the next scan. And so it can continue. Okay. So the robustness is really one of the key parts there. Matteo, did you want to add anything there?
No, it's fine. Thanks.
Cool. So this is some really great analysis from Matteo and some great tools there. Any questions for, yeah, okay. So that's kind of on the Lidar front end. So if you want to add anything there, Matteo, it's a good time. Otherwise, if there's any questions on that, Matteo could answer them now.
Then I actually have one question for the bottom one. So for your approach, you don't use any depth information beyond Lidar, right?
Correct, yeah. So the only sensor sources considered here, and Matteo, correct me if I'm wrong, is there's wheel inertial odometry, there's IMU, and there's Lidar.
So, but there's no visual in any of, in Lofi at the end of the day?
Correct, yeah. And for these test cases, there's no visual, yeah.
Okay, just to clarify.
But that's right, I think, and so Matteo has a lot more results on testing on spot, where the odometry we feed in is visual inertial odometry. And so that's something else that can be used to have it, and that's the same idea of having different sensor sources for robustness. Cool. Thanks.
Yeah, thanks.
Any other questions on the Lidar odometry? Cool. Okay, thanks. And again, Matteo's got a lot more details on that, and there's an upcoming paper that's about to be released, or at least submitted, and hopefully we can put it on archive soon, that we can give you details on. Next up, I wanted to move on to the global localization. And this really, the primary odometry source we tend to use is from Lidar odometry, because that looks often is the most accurate. So I should clarify here, these results are with no loop closure. This is purely just Lidar odometry. It has a map that it matches to, but it's not doing any loop closures or any optimization in terms of the SLAM side we typically expect. The SLAM side is what we have here. So we want to get a global location, a global map, as well as reporting the global position of the artifacts. And we call this LAMP, Large-Scale Autonomous Mapping and Positioning. And so it is really the back end of the global localization, so doing the optimization and handling combination of sensor measurements. It's agnostic to odometry input. It doesn't have to be Lidar odometry, it can be any odometry input. We have methods of doing loop closure, and it can have multiple methods. It's extendable to more methods. It's based on postgraph optimization, which I'm hoping most of you guys are familiar with, given you're in Luca's lab, and designed to be extendable and multi-robot. So I assuming you guys have a reasonable understanding of postgraphs. I'll go through a little bit of an introduction, but also to introduce kind of the concept of how we go about it. So we have these different nodes in the postgraph as our different robot poses. And they're the variables we want to estimate. We also have these factors between them, which are our measurements, essentially. And so the measurements we use for the LAMP is an accumulation of odometry. And normally we accumulate odometry to roughly 1 meter. This is so we have a fairly sparse graph. And so this factor is accumulation of odometry over that time. That could be multiple sources of odometry depending on what we input, but let's say, for instance, Lidar odometry over 1 meter. And so that's, this is, I guess, a formal description of all the measurements that we have. And this, this optimization is essentially what we're doing with the Lidar odometry front end. Given our 2 measurements for Lidar scans, we compute the odometry that best aligns them. But then, again, accumulated to be roughly up to 1 meter. Now we also have Lidar scans at each of these nodes. So we can call them keyed scans because they're kind of at key nodes, which we seed a new key node once we pass that 1 meter threshold. But these keyed scans help us to build up a map, but also we'll use them later for loop closures. So if we look at the single SLAM problem, and it's kind of typical formulation here where we're optimizing our motions, poses, and map given measurements. We kind of separate the estimation of the motion by using any odometry input. And then we estimate mainly the map and the pose with LAMP. And it's all based on postgraph optimization. So, and again, I'm not going to go into too many details on that. I'm assuming you guys have reasonably familiar with postgraph optimization. But if there's any questions on things that are unclear, please jump in. So I'm going to go through now a bit of the overview of the structure of LAMP. And so we have LAMP robot here, which is the main process for running LAMP on the robot. And basically this main kind of central, in the ROS sense, it's a separate node, but let's just say it's a separate process, is to manage the postgraph, to manage everything that goes in the postgraph as we add these measurements in. And so the main thing is taking these factors from what we call an odometry handler. So our main step is using the hero odometry. This is so you can switch between odometry sources, but most of the time in good conditions, the hero odometry outputs Lidar odometry. Once we accumulate that over 1 meter here, then we give just factors and just information for factors to this central postgraph management process. And then we get the point cloud associated with each keyed node. So we get the keyed scans, as we call them. But this is also, we've designed LAMP to be modular to enable a whole different type, an extendable amount of ways we add factors. And so we call this an odometry handler. We can also have artifact handlers where we take in artifact messages and add them as factors to the postgraph. The idea is we can have any number of handlers for adding different types of information to the postgraph. And so this is a representation here, credit to Luca for making this, but I'll build it up as a way of showing the different components of LAMP. So we have each of the robot poses, odometry between them, which could be from visual or Lidar odometry, and some observations of artifacts. So this is a example of what benefit we get from using Hero as the input to LAMP. So this is testing in an office environment. And so we have areas with very flat walls and some corridors that are pretty much featureless, straight walls, straight floor, straight ceiling. And so as we're testing in here with the Huskies, we have areas of what we call Lidar slip. So that's basically, you can't tell if you're moving forward and backwards. That movement's unobservable. So as we drive through here, we get Lidar slip. The robot isn't moving on our views, but in reality, it was moving. And you'll see it, we do one full loop and we come back to the same place that we started. And so there's features in a lot of the other places, but we stop here. And you see we've got about 9 meters of error from our Lidar slip. So instead, we have a Lidar slip detector, which is some work I know that Andrea has been looking at as well. And that detects when either a difference between wheel odometry and a Lidar odometry, or the low observability of the Lidar. And that sends a flag to Hero to say Lidar is not healthy, and then it switches to using wheel inertial odometry. And so what that looks like is we switch to wheel inertial odometry, so we keep going. It's a little bit less accurate, so we drift a bit to the right. And then we see features and we switch back to Lidar odometry. And so as we go around, we get just 1 meter of error. And then I think, is this the same line? Okay, yeah, it's the same, cool. So, but over long traverses, we have multiple kilometers, we have requirements for very low drift for scoring in this competition. You have to detect artifacts within 5 meters. So we need more than just odometry, hence we use loop closures. And so the idea here is that we might have odometry nodes, and then let's say this is a keyed scan around it. As we progress, we may have some drift, but then we can search for nearby nodes to see if they've got a matching keyed scan that can say, okay, this is actually the same place. We can identify that and then do a loop closure. Now, on the theoretical side of things, why are loop closures helping our optimization of the postgraph? As we start off with a unary factor, our prior, this is where we're most certain where we are. And these blue spheres represent kind of a pictorial representation of the size of our uncertainty. As we go further and explore further, this uncertainty grows. So it's largest the furthest from the starting position. But if we then have a loop closure, that reduces the uncertainty because the distance from this starting point to that node has suddenly been decreased. And so we get that reduction in uncertainty and hence improvement in the estimation of the node positions. So for loop closure, in the basic sense, we just do a local loop closure search. So as we've driven out this way, as we come back, we look within a radius for nearby nodes, nearby key nodes, and then take the key scans and do ICP. The ICP serves 2 purposes. The fitness score can be a criteria to accept or reject it. So it's kind of detecting, is this actually a loop? And then the transform gives us the factor we can add between these nodes. So we add the loop closures in. And the way we do this is using some great work from your lab, which Yun has been the master of, is using Chimera robust postgraph optimization. So when we want to optimize our postgraph, we send this to Chimera RPGO and we get back the optimized values, which is managed in this node. We choose when to optimize based on a loop closure process. This loop closure takes in information of the postgraph and keyed scans, and then gives back when there's loop closure factors. This can be the loop closure I described, but is extendable to be anything else. It could be visual loop closures as well. Once there's a loop closure, then we go to the optimizer and update the values there. And so here's some examples of loop closures we're having as of the tunnel competition. So this is driving around in a mine, 800 feet underground in West Virginia. And here we are mapping out the environment during the tunnel competition. You see the environment here. This is the map we're building up. It's about 200 by 200 meters. And then you can see at the bottom here is the kind of closer zoom up, not necessarily time synced, of the environment we're mapping. As we go around, we're going to get a fairly decent and consistent map of that environment. This is a Beckley exhibition coal mine, another mine. And this is going to show some of the benefits of loop closure. So we've driven around a fairly long distance, about 200 meters with the bend. And then when we come back, we've drifted a bit. And so up here, you can see at the top of the screen, we have the loop closures to be able to correct that map. And that improves the performance there. However, there's some areas where loop closure could be improved. This is still showing very strong performance over a long distance, but we have some drift. and it's better than having no loop closures, but we can probably make some improvements in different areas. But we also leverage the outlier rejection from Chimera RPGO. So as we come back down in this loop here, outlier rejection keeps this consistent, whereas without outlier rejection on the right, you see that we have some bends in the map. So that's some great work from you in there. So that's the technologies we have, and that's published in a paper that's going to ICRA as well, a LAMP paper there, which I'll show you details at the end. But we're looking at ways to improve loop closures. And so I was going to throw out two ideas here, but given we're short on time, I might just push forward. But we want to find more loop closures, compute more accurate transforms, and have fewer false positives. And so at the moment, we just use GICP for the alignment and for the testing. But an improvement, kind of led by Ewan and Michelle working in Luca's group, was to accumulate neighboring keyed scans and use feature-based initialization to get the initial alignment, and then do GICP from there. And that's showing really great improvement. And so you can see some example of this here. This is the same example you saw with the Lidar slip as it gets back, but then we drive forward a bit and we have that loop closure that corrects the map even better. And bang, we're back to a perfect map. We have some other environments. You've got multiple robots driving around, but I'm just going to get you to focus on one of the robots. Just focus on Husky 2. So it's gone through a corridor where it's switched to using wheel inertial odometry, so it's drifted a fair bit. And just look at the robot down the bottom right. As it's driving around, it's got a lot of drift, and so the map's not looking great. But it revisits where it was before, and it's able to detect quite a large loop closure, make a big correction, and then really improve the map. And it continues to do a few more passes of where it's been before and make some more loop closures to make some more corrections to the map, to correct something that was really looking quite bad. And so it's kind of just showing the benefit of loop closures when we're having some issues with odometry. But there's still some improvements we can have, which we'll come back to a little bit later. And yes, I did say multi-robot. What I've been describing to date has just been a single robot. And so don't go into too much detail on this, but basically what I show is the whole system we've described is represented pictorially in another way here, but for different robots. And so we have like robot 1, we have same thing for robot 2, and same thing for robot N. But they all go back to one central base station. So it's very much a centralized architecture. And that kind of really suits the problem, because in the end, we need to get it back to the human operator. And so we need to get the information there anyway, so we may as well centralize the computation where that gives us advantages. And so when we have this single robot architecture, what we actually have is sending the pose graphs and the keyed scans to the base station. And so we have another robot with all the information, same information on the base station. And this base station builds off the same code base as what it would be for the robot, with this central pose graph management. But instead of taking in odometry from an odometry handler, it takes in the factors and keyed scans over the communications from every robot. It similarly has the same optimizer, exactly the same setup. But for the loop closure, it's a similar idea, but it's a multi-robot loop closure. So it takes in new pose graph nodes and keyed scans, and then looks for loop closures, not just within a single robot, but with multiple robots, and then sends those factors back for optimization. And so then we get these inter-robot links here. We also send that multi-robot pose graph back, which is mainly for planning, so we can go somewhere where another robot's been. And we also have an interface with the operator, because we're on the base station, we have an operator there, so we can suggest loop closures, but we can also ignore a robot that's going bad. It might have a bad sensor to stop that going in the optimization. So here's an example here of that happening. So this is the same environment as before, the previous video, but doing multiple robots. And so Husky 3 is drifting a bit because it switched to wheel inertial odometry, but then it comes back and revisits where the other robot is, and we get a great loop closure that corrects it between the multiple robots. So it's revisiting where another robot's been is able to really improve the graph. Likewise, Husky 2 has some improvement to the graph from revisiting where Husky 3 was. And so it's kind of showing that some of the benefits of that multi-robot loop closure when we're exploring large environments. Now this is it operating in the urban competition. And so I'll jump through a little bit through this video, but 4 robots are starting here, and we're going to go and explore this environment. first off, we send a husky. Oh, let me just jump back a bit. And so that husky is going out and exploring the environment. It chooses to go down. There's a junction here and explore this way. We have a second husky that's coming up. And that goes and explores this way. So we have a split of where they're exploring. So they there's a lot of loop closures along this initial corridor, but then they split different directions. And so they continue to explore. They're coming around closer to each other, but no additional loop closures yet. We have a spot going up the right-hand side. Again, there's loop closures in this initial corridor. And then spot goes to a stairs. We have a second spot, which is causing issues. It had an error in the sensor. And so we chose to ignore it from the optimizations. Meanwhile, the two huskies, these two here, are coming close together. And eventually we have a few more loop closures here, keeping the graph to be consistent. The other spot went downstairs in the meantime and is creating this map underneath. So you get the multi-level mapping. Obviously, there's less loop closures when it's a different level, but these two huskies had loop closures together. And I don't have it now, but the map without loop closures was quite messy. So there's an example over an environment, and this is again about 100 by 100 meters, roughly. So that's kind of the performance that was in the previous competition. Coming back to other ideas of loop closure improvements. So that we limited somewhat by searching locally, and if there's large drift, we could have some challenges there. So one of the ideas we've integrated is using dropped ranging beacons. And so these beacons here is the comm nodes, but also this white box here is a UWB beacon, ultra wideband. So it gives ranging measurements between the beacons. And there's three different ways we're looking at integrating this. One is so just take a step back. These UWBs are normally used for localization in a known environment. So you place a lot of beacons around and you get triangulation to track the position of one beacon. But in this environment we're going into, it's unknown. And so we have to drop these beacons and use that information from dropped single range beacons, or a single range measurement to one beacon, is guess what I mean. So we thought of different ways. The one is using a between factor when we drop it, so we kind of know where we drop it, and then integrating range factors directly to the post graph. Second way was using kind of a process in the range factors to compute a triangulation of the delta between different nodes and adding those factors. And the third method was using it as more of a detection of loop closures. So identify when we're close and then search for loop closures with our Lidar ICP method between those nodes. In the end, these two methods are quite challenging because in 3D, there's a lot of ambiguity with the type of range measurements that we get with a single range beacon in the types of environments we travel, where it tends to be mostly along a straight line. So this was the most robust method, and it's basically a very robust way to detect loop closures. We then use the Lidar to get the transform. And so that integrates into this architecture by another handler, but that just directly gives measurements to, or I guess suggestions to the Lidar loop closure of which nodes to look for loop closures between. It also sends that information back to the base station. So the base station gets the UWB measurements and it processes them, and then it looks for multi-robot loop closures. And so that is looking for maybe one robot dropped the node and another robot drove by it, and it uses that node to say, okay, you've definitely passed by the same place, let's look for loop closures there. So it's kind of a way that can detect loop closures with a high confidence. So the next steps going forward, this is kind of a very quick overview, and I'll throw to questions soon, I'm almost done, is looking at the Chimera loop closure to integrate, and maybe using teaser, like from your guys' lab, to do initial loop closure alignment. So looking at integrating some of the great work from your guys' lab. And don't have time for this video, so I'll sequence to this slide, but you can see Yun's the star of this video. These are some of the papers of what we talked about. These two are submitted. This one's coming up in ICRA, and these three are going to be submitted soon. One on using the ranging beacons, one of Mateo's work on light odometry, and one on the artifacts there. So I'll leave that up in the 2 minutes left sequence to any questions you guys might have. I'll try to go through the chat as well. But hopefully it gives you a bit of an overview of kind of how LAMP works and the different components that there are in SubT.
And was Great overview. Thank you so much for giving this presentation. Actually, I was thinking that, in the lab, we often focus just on the algorithmic side of things, and was kind of refreshing to get like a system view of how these things come together. Was really refreshing. Was I think very useful for the students as well, who sometimes like are focusing on their work on a specific block in the architecture, but they risk to lose the big picture about the architecture. So very, very interesting. Before kicking off, the Q&A, I just wanted to say it's been a great pleasure working with you guys over SubT. We are very excited about the continuation of these and the next round of the challenge. But it's been a lot of fun for me, and I guess for you and the others involved. In terms of Q&A, I guess the procedure that we typically have is either you guys can post questions on the chat, or you can just unmute yourself, raise your hand and unmute yourself and ask the question.
I have a question.
Sure.
Go ahead, Jim.
So, well, I can kind of see on your citation, but what is the frequency range for the rangefinders you guys have? Is it ultra wideband?
Yeah, the frequency range, I'm not too sure. I think it's ultra wideband.
Okay.
Yep.
Yeah, ultra wideband. Yeah, got it.
So
have you guys tested different kinds of ranging beacons, like radio waves?
No, we haven't. No, we haven't.
Okay.
That'd be interesting to do. We're using, so they give metric ranges. So they have a way, I think they encode in the phase or something like that. So you can kind of get, you can actually get the time of flight to get centimeter level range. Whereas we do have these comms beacons. So we're thinking about, we do have like signal strength for those. So you get pseudo range from them. So we're thinking about using that as well. I
see. Also, it looks like you guys are using deca wave sensors. Is that correct?
That's correct. Yeah.
Okay, I see. Have you guys tested its performance in different scenarios? Like, for example, I imagine this one you guys are using it underground. Have you guys tested like how the air moisture affects the attenuation of the signals?
Interesting. No, we haven't. We kind of tested different like orientations, like if it's lying flat on the ground, if it's up like it is here, to kind of see what the rough range would be. But haven't looked at kind of the different environmental conditions of what the attenuation is. I think a lot of the environment obstruction is fairly extreme. But yeah, it's a good point. Good point.
Thank you.
Then I had a small question about, maybe you said it already because I arrived a little bit late, but are you planning to open source anything there?
Great question. I want to. Realistically, I don't think Ali is going to let us until after the competition. But I think, yeah, I'd like to. And I'd like to kind of spend time making something that is extendable, and like, especially because we're trying to get LAMP to be fairly flexible to the type of input. And I think the work Taz done with Lidar Odometry is something that'd be great to be open source for people to use. We're trying to make it very practical for use on robots. But that probably won't be until after the competition is finished, or with enough time that it's not going to give any advantage to other teams if we release things that they can use. So yes, but still needs to be discussed with Ali, who's the PR.
Yeah, and awesome presentation. Thank you.
Thanks.
So guys, I'm seeing a question from Josh on the chat, which is, I will read here. So why using Hero instead of a Kalman filter or a different sensor fusion technique? And maybe what do your confidence measurements for sensor data look like? I think that's
Oops, sorry, look again.
Yeah, I think clarifying the Hero versus sensor fusion and saying a little bit more about the type of checks, I think would be very interesting here.
Yeah, that's a really, really good point. Thanks for that question. So it's kind of two different philosophies, right? There's, if we go back to here, there's either multiplexing or fusion. And it's in Hero, but it's also in Lidar Odometry. The benefit of fusion should be increased accuracy, but the downside is it comes along, at least in our experience with the algorithms we've been testing, with heightened sensitivity to failure. And so if one of these sensor sources goes wrong, that has a high chance of corrupting the solution. Now, there are methods and approaches where you could appropriately, if you can catch it and in a quick enough time that, for instance, catch that VIO is failing and have an appropriate way of adjusting the covariances, or have it modeled in a way where you can kind of see that your features are drifting and drop the covariance down so it essentially gets ignored. That's one approach. But if that doesn't kick in soon enough, then you can have a bad measurement coming in and corrupting your fuse solution. And so the approach we have of kind of multiplexing with Hero is based on kind of a need for that robustness, that we can handle it going wrong for a little bit, because it's not going to corrupt our filter, it's just going to drift, and then we can switch to something else. And so that is a way that we're seen to be more robust. So my computer froze a little bit there, but does that make sense? And then I'll jump to the question on confidence checks, which is a really important part of it as well.
Yeah, I think it's a problem of outlier rejection, right? And I guess what you're saying is that instead of performing an outlier robust fusion, in some case it's easier just to multiplex. And I would agree with that, at least in a first implementation, because I see the challenge of setting parameters and making sure that you adjust the covariances. I think what the students have to realize is also that there is a little bit of difference. Like, here we're shooting for a really robust deployable system. So often in this case, you prefer a simple solution, which maybe sacrifices a little bit of accuracy with respect to a complex solution, which is tough to implement, can have bugs and so on. So there are multiple considerations that needs to be factored in the design, which is something that I really enjoyed out of the project. Is system level take on the robotics problem, which is very interesting.
That's a really good point, and I think it's the fused approach is kind of like the quote unquote right approach in terms of what is the best way to do it. But then there's the most practical way that can be deployed in a system that needs to operate robustly at any moment in time, in 6 months, to get that ready in 6 months or in 12 months. And so that's kind of where it's skewed towards what's practical to have everything together and working as a full system in a short space of time. And so I think that's, Luke hit the nail on the head there. To touch on some of the confidence checks, which is an important part, whether we could be part of a fuse method or the method that we're doing, is to, there's a few simple checks, which is kind of the rate of the output. We're mainly doing checks on the output of the odometry algorithms. But and it depends on the algorithm, but some of the things are looking at the covariance coming out. And so if we look at the trace of the covariance, we can see if it's starting to drift from some of the VIO methods. We look at the observability of the Lidar inertial odometry. So that's some work that Andre was doing, which kind of looks at assessing the normals of all the scans around and looks if there's an unobservable direction. Otherwise, is looking at the rate and the presence of them at the moment. And so there's definitely some scope there for some more research on health checks on using different components, such as looking at numbers of features tracked in the visual odometry, looking at kind of the maximum minimum ranges for Lidar. But I think the most value comes from looking at the covariances if they're appropriately handled in the algorithms. And I think one paper to look at, I think, which is interesting, is if you look at VLOAM, it's kind of similar to what we're doing, but they do a more of a fused, robust approach where they do use some of those observability metrics and change how they're fusing things. But yeah, well, I guess we're trying to use the algorithms we know that are robust and work, and then just switch between them for the same reasons Luke was mentioning.
Thanks, Ben. So let's see if there is no other question for now. I have one question I have to ask. I know it's late, but I'm curious about your take on that. Mm-hmm. So I think right now, we are easily running these with let's say 5 robots, maybe in that ballpark. Mm-hmm. If you're trying to scale this up to 50 robots, what is the first thing that will break or will become a bottleneck here?
Comms, and then the base station processing. So. So comms is.
What's your guess about the current number of robots that we can support in these two, from these 2 points of view?
So I think comms could probably take up to maybe 10 robots sufficiently. after that, the kind of the bandwidth becomes a bit more challenging because it's all through a mesh and it's coming back to one location. But I think the other one, which I think is compelling for where we go moving forward on the LAMP side of things, if we look at LAMP base station, which I'll try to bring up here, I think it's when we're processing, so there's a lot of information coming through. We have many more robots coming through, and when we're processing these loop closures, it can get really backed up if it's having 5 scans a second coming from 50 different robots or something like that. We can have a really beefy computer on the base station, which can help. But I think then that's probably a compelling discussion for kind of having more on-edge computing and doing the distributed SLAM side of things. So I think we can probably handle maybe, with the current computer, probably up to like 6 or 7. But we're trying to get a better computer on the base station, which we can handle 10 or more. But I think that's where it'd be very compelling to push for distributed SLAM, which I think this architecture and Luca and I've discussed before could be extendable to that. It's just that we're not at that numbers of robots yet. So once there's a motivation to do so, I think that'd be a really interesting area to push.
I think that's a great answer. I mean, one perspective is about the resource utilization. The other perspective is also about how effective, like, there is a diminishing return, right? You can, if you keep scaling up the team, at some point will become just obstacles along the way. So, but I appreciate the answer. Actually, it's very interesting.
Cool. Yeah, that's a good point.
Okay, guys. If there are no further questions, I think
I have some questions.
Andrew. Yes.
Yeah. So the first one is more of a logistical one for the base stations. You're going down and you're dropping them off. Can you pick them up again?
The communication nodes?
Yeah.
No.
Sorry, not the base stations. Yeah, the little things that you drop off your robot.
Yeah.
Landmarks.
So we don't. The reason, I guess, we kind of to do motivations for the competition, they collect our stuff after the run, so we can just drop them off. But in the context of search and rescue, that we could perhaps see them as an expendable thing if it allows us to get down there and save someone's life. So we could just leave them down there.
Yeah, that makes sense.
We also currently don't have to get the robots back to base, although we theoretically could do that. It'd be an interesting manipulation challenge to pick up the nodes, but that could be an interesting avenue to look into as well.
Yeah, definitely. How expensive is one of these little beacons?
So the node, the white node, which is the UWB, is fairly cheap. I think it's about, we buy them in bulk, so I can't remember the exact conversion, but it's like $100 or something like that. Not too expensive. The black node is like $15,000. So that's like a military grade communications thing. So that's, if you buy it off, just commercially. I think we've got a partnership there, but yeah, they're a lot more expensive. These ones are fairly cheap.
Makes sense. So the second question is about vertical drift. Do you ever have issues with the vertical drift while you're navigating these terrains? It seems like the wielded robots are mostly going over flat surfaces, but at one point you had Spot go downstairs to explore a second floor. And I was just wondering how planar your reconstruction is.
Yeah, that's a really good point. And that's a really big challenge that we're working on in Matteo is looking at the moment. So this flat ground assumption is something that we use to help kind of constrain the Z drift, because often the LiDARs are mounted in a way that's hard to observe that movement. In terms of if your LiDARs are mounted as kind of a LiDAR typically is, with if you see the LiDAR here, it's kind of flat. You don't see much up and down of the movement. So yes, it's spot on as one of the big problems. In terms of so that FGA definitely helps, the flat ground assumption. But for the Spot, we also have this. We turn it on, but we have a stair mission when we're going down the stairs, and that stair mission deactivates FGA and then reactivates it. So for each floor, we can kind of keep it flat. Just need to navigate down the stairs. Seems to be okay. The stairs are very challenging, but that 3-step approach I was saying, we benefit from having very accurate initial external odometry. So Spot has a kind of inbuilt visual odometry, which also utilizes the kinematic odometry, which is basically looking at all the limb movement and kind of using that to track how it moves, which is incredibly accurate. And it's got a fusion of 5 real sense cameras around it to track the odometry. So it's not as good as Lidar odometry throughout large scales, but locally it provides a really good initial estimate for quite aggressive movement. So it can capture the high rate, which then makes our Lidar scan actually more accurate. So I think that helps us a lot for that movement down the stairs. But it's something that we're really working on at the moment of how to be better for Z-drift, using the IMU in more ways, in LAMP or in LO, because cave environments, we anticipate there's a lot more Z movement and probably no flat ground.
Yeah, great. Yeah, this was really cool, by the way. So thanks for giving the talk.
Thanks, man. Appreciate it. My pleasure.
Really second that was a terrific presentation. It was super informative, and I will probably stop here. Sorry, Ben, in the interest of time, I'm sure you have to go to other meetings. We really appreciated your time and giving this presentation, and we look forward to collaborating more on SubT.
Yeah, likewise. Thanks so much. As I said, it's a pleasure to present to you guys. I'm on the Slack channel for Spark, so feel free to reach out, or there's a LAMP channel as well. If you got some questions, I'm happy to answer them. But yeah, also to present to you guys, and I guess just finish up by acknowledging the great work. I'm presenting what is a large team's work. So Mateo, Yun, a lot of Michelle also working on things, and a big team of people back here at JPL. So it's kind of amazing what everyone's putting together, and it's great to be able to share the great work that everyone's done.
Fantastic. Okay, thank you.